Hi, my name is Madison Krotzer, and for my term project, I designed checkers. There are a couple different game modes that you can play in, the first being split screen, where two human players can play against each other on the same screen. The checkerboard works by actually clicking a checker and dragging it to the new space you would like to place it, and then clicking again to put it down. You cannot make a move that's illegal, so it's Blue's turn right now. So say I were to try to move forward a space instead of diagonally, it will drop my checker back where it belongs. It doesn't change moves or anything, but the player can only move their checkers to a legal move spot. Next I'm going to show you one player. For my one player, I made an AI using a minimaxing theory, which I'll talk more about later. There are three different difficulties: easy, medium, and hard. The difficulty actually affects the recursion depth that the AI goes to. So easy goes to a depth of 3, medium 10, and hard 15. The AI isn't necessarily constrained to automatically jump a piece if it's available. It's not forced to do anything. It is evaluating every possible move from a state, and from there it decides which move is best based on an evaluation function, which I'll show you now. This function here, called digit scoring, is the evaluation function for the minimaxing. The first thing it does is check to see if a game is over. If the game is over, it will return a very large number if the player has won, and this encourages the AI to make the move if it will end in a win of the game, and a very large negative number if the player lost, and this stops it from making a move that will lose the game. If the game isn't over, it goes on to count the number of pieces on the board, first for you, and you get points first for the AI, and you get points if the piece is on the board and depending on how far it's moved from the home row. Pieces that are farther up are closer to being kinged, and to encourage the AI to continue moving forward on the board, it gets an extra point if the checker is a farther row ahead of others. It loses points for every checker that its opponent has. It gains extra points if it's a king, and loses extra points if its opponent's a king. This encourages it to go get itself kings and to stop its opponent from getting kings, as well as to jump the opponent pieces. The AI minimaxing is actually working with a digit board as opposed to a 2D list. For the rest of my project, I did navigate a 2D list for the split screen and the multiplayer, for example, but in the AI, I turned the 2D list into a 64-digit long number, each digit representing a space on the board. And that allows me to do operations much faster, and speed is key with the minimaxing, because minimaxing takes many moves and we'll have to evaluate hundreds of boards, so anything we can do to make it faster will keep the game working well. If you look here, if I move over to my hard level with a depth of 15, it still can work and make a move within 10 seconds. The same holds for my easy and my medium. One of the things I had to do for the medium and hard modes with the greater depth is to start to use alpha-beta pruning. Alpha-beta pruning, which is down here, takes advantage of the fact that you don't need to check every branch of a tree that you create while minimaxing. So while actually creating a minimaxing tree, what we're doing is we're making every move possible, and then we're, from each move, letting the opponent make every move possible and checking the scores at each level of the tree. So our tree goes back and forth between levels that are max nodes, where our player made a move, and levels that are min nodes, where our opponent made a move. So we want the opponent to have the low score, as well as us to have a high score. What alpha-beta pruning actually does is, if a branch on the tree, for example, if it was at a depth of 1, our first max node, had a max, if one of the pieces of the max tree were to go off and have branches of min nodes that were higher than the max nodes on a different piece of the layer before, the max node with the low score is going to be ignored for the rest of evaluation. This allows us to cut off almost half of the total boards that we need to evaluate, and it greatly increases its speed. When I first started working with this, I started to slow down and have enormous wait times after a depth of about 5, but alpha pruning allows me to get to 15 within a reasonable amount of time. Alright, now I'm going to show you my multiplayer. This works using sockets. I've used my terminal to pull up 2 separate windows. I currently have it on a local host, but it does work with non-local on 2 computers. So I'm going to host a game on this left screen and join the game. As soon as someone has actually joined the host's game, it will automatically bring them to a board where they can play. So when it's Red's turn, Red's allowed to move on their board, and as soon as Red moves, it will automatically be sent to the blue board's screen. If I attempt to move a piece when it's not my turn, so if I go over here to the blue screen, and it's Red's turn, and I try to move a red piece, I can't, as well as if I try to move a blue piece, I can't. When doing multiplayer, I actually sent over the entire board as a string. That way, if we have a move such as a jump, it doesn't interfere by not taking pieces off the board, and the entire move is sent. Alright. Now let's go back to our checkers. Next I'm going to show you about my save function, and this one used file IO. So for now I'm going to go to my split screen mode and start up a game. If you'll take note of the board, I'm now going to save it, and if I save my board, I can exit out of my program, come back at any later time, reload, and if I just hit load game, it will load that